Let's look at an example of a rational function that does not have a horizontal asymptote. This one. Notice that the degree on the top is bigger than the degree on the bottom, and this would mean that there is no horizontal asymptote. However, we can still study the behavior of this function as x goes to either negative or positive infinity. In other words, as x is going to infinity, we can say, what does this function start to settle down to? As x is going to negative infinity, the same thing. What does the function start to settle down to? And we'll call that the slant asymptote. But before we get to the slant asymptote and how to find that, let's go ahead and find the usual parts of this, the y-intercept, for example. We put in a 0 for x, and we find the y-intercept is 6. So we've got a y-intercept of 6. Now let's find the x-intercepts. We find that by setting the entire function equal to 0, which just, one step more would give us that the numerator equal to 0. Because we would, in solving this, we would multiply both sides by x plus 1 and just get the top equal to 0. So we've got x squared minus 7x plus 6. That's a factorable quadratic equation. Factors this way. So now we get our two x-intercepts to be 1, 0 from here and 6, 0 from here. Now, there's no horizontal asymptote, but there is a vertical asymptote. The vertical asymptote, we find that by setting the denominator equal to 0. X plus 1 equals 0, and that's a super easy equation to solve. X equals negative 1. So now we have our vertical asymptote. Now let's look at how we find our slant asymptote. To find the slant asymptote, what you want to do is just divide the top by the bottom. Now notice the degree on the top is 1 bigger than the degree of the bottom. So when we do this division, we're going to get a line. And that's going to, and that line is going to be, well, let me not get ahead of myself. Let's go ahead and do the division and we'll check it out. Instead of going through all the processes here, I just pasted in here the final result of our long division. We've got x squared minus 7x plus 6 divided by x plus 1. And when we finish, we get a quotient of x minus 8 and a remainder of 14. So here's what this would look like. What we're saying is x squared minus 7x plus 6 divided by x plus 1 equals this. This exactly. Now, we can look at this then and say, okay, we're wondering what the function looks like as x goes to either negative or positive infinity. We're looking for the extremes. Well, think about this. Let's just think about as x is going to infinity. What happens to this thing? In particular, what happens to this term here? Well, x is getting larger and larger and larger. And that's in the denominator. The numerator, it's just staying put, 14. It's not growing. So you have a 14 that's just constant divided by an ever-increasing denominator. Well, this is just going to go to 0 then. This whole term here is going to fade away. It's going to go to 0, and what you're going to be left with is y equals x minus 8. This is what this quotient, this is what this thing settles down to as x goes to infinity or negative infinity. It starts to look like this. This is the slant asymptote. Notice what we do is we do the long division and the quotient here. That's our slant asymptote. Now here is what the graph would look like. Notice there's slant asymptote right here. And what happens is as x gets larger and larger, the function settles down to this slant asymptote in both the positive and the negative direction. And here's our vertical asymptote here. Here's our two x-intercepts, and here's our y-intercept.